and z is equals to 0. That is why I said the first point will be 0 for x and z will be 0. The point that we will be working to find out is the y. So, and the y is given again is that we had been told that it's at point 403, and therefore our y was 0. And therefore what you observe is that the perpendicular line that is joining our point of observation to the y line is simply placed at y is equal to 0. And therefore that is how I obtain my point, the source point to be at 0, 0, 0. So what I do is that I just now minus R3 minus R2 becomes 403 minus 0, 0, 0, we get 403. And this gives us the vector 4ax plus 3az. The other point that we of course need to find out is R23 modulus. And R23 modulus is simply the square of each term, 4 squared plus 3 squared, square root, you get a 5. That becomes straightforward. So what we are saying is that from our figure here, the direction or the length of the line perpendicular to a y-axis is simply having a length of 5. That is what we needed. So we now, once we have found that out, we just, to obtain now our final item that we are looking for, which was A, or the unit vector AR23, you simplified the length R23 divided by the magnitude, which is 5. So you say 4ax divided by 5 plus 3az divided by 5. That becomes our point AR23. Therefore, we now plug them in to our equation. Remember, we had this row is the same as the one we have found to be R23 magnitude. We have found it to be 5. So we are just plugging in that value and this value here. Therefore, what we are getting is that this was, we are already told 3 pi times 10 power minus 3. Then you plug in your value 4ax plus 3az. Our 5 is here, and what was the denominator here, I just placed it here. Therefore, when you solve that, then things become a bit only mathematical remaining, and we end up with 6 over 25 ax plus 9 over 50 az millicoulombs per meter squared, and this gives you 0.24 ax plus 0.18 az in millicoulombs per meter squared. And when you get that, that is the value for dl. And of course, you can see it is the same value that we found here. And therefore, the total electric flux density that is acting on this point of observation is simply the sum of the two, dq plus dl. And when you add them, remember some of them are in millicoulombs per meter squared. So you of course you add them and you get this final value at that point. So that serves as an example, so that you get to find out to know the actual meaning or the significance of electric field strength density. So okay, or the flux density, which is expressed as d as d. So for that, I guess it's clear. Unless you have a question, I pause a little bit so that we can confirm that nothing is too much for everyone before we proceed to section 4.5. I also take a glass of water. We start again on Gauss Law. It's a new subtopic that is similar to the Coulomb's law. And Gauss Law is developed by a German mathematician called Carl Gauss, or Carl Friedrich Gauss, that developed the divergence theorem. So this is the same, the material that we discussed on divergence law or divergence theorem is the same person who gave us this Gauss law. And the Gauss law states that the total electric flux psi through any crossed surface is equal to the total charge enclosed by that surface. And in very simple terms, you have a cross surface that has some charge Q, and you have now flux that is flowing. The flux that will go through this volume or this cross surface will be equal to, remember that we said the flux is measured in terms of coulombs. And both charge, or rather, charge as well is measured in terms of coulombs. Therefore, we are saying that if we have one coulomb here, and you said one coulomb is equivalent to one flux line, so then you're saying that one flux line will manage to pass through this, get in touch with my charge, and then come out. If there is no, if completely there is no charge inside this cross volume, then no, then no flux will get inside there. They will just bypass it. Okay, that is the meaning of electric, or rather, that is the meaning of Gauss law, that the total electric flux that is cutting through or passing through a cross surface is equal to the total charge enclosed in that surface. So then some illustration, just like I have discussed earlier, and applying Gauss, or applies the divergence theorem. You can actually, if you remember the divergence theorem, it is stated, this is actually the statement of divergence theorem, in case you might have lost or you have missed out. This is the divergence theorem. It states that the cross surface integral of a vector D over the cross surface is always equal to the divergence of D over the volume. And therefore, if you apply just that rule, we are saying that we can find out that the volume charge density, if there is a volume, it has 10 coulombs, and it is of 10 meter cubic, then that the density of that volume, or the charge density, is equals to 10 over 10 becomes 1 coulomb per meter cubic. This is the one we refer to as rho V. So we are saying that if the volume charge density enclosed in a volume is equal to rho V, then the divergence of D is equivalent to that, or they are equivalent. Or the amount of flux that are passing through that is simply expressed by divergence of D. So just remember that to be the case. So I think that illustrates what the Gauss law states. There are some observations that we can make from that. That equation 4.1 and 4.3 are basically stating Gauss law in different ways. So equation 4.3 is a statement of Gauss law, as well as equation 4.1. But equation 4.1 is the integral form, and this is differential form, or what we also call point form. So that is how you state the divergence. Of course, you notice that the differential form is derived using the divergence theorem. And the integral form is purely coming from the definition that says the charge enclosed in the volume equals the flux that is flowing through the volume. Just like I have mentioned, that flux enclosed, or the charge enclosed is equals to the flux flowing through the volume. And from the definition of the flux, which was we defined earlier as the electric flux passing through the surface, then we're saying that equation 440 comes as follows cleared from this equation, and therefore we end up with equation 441, that is definition of the Gauss law in the integral form, equating the volume charge density integrated over the volume to the volume that is enclosed. And then equation 443 that describes the divergence of B as equivalent to the volume charge density. So the other point that we should observe is that Gauss law is an alternative statement of Coulomb's law, just states Coulomb's law in a different way. And it is we are actually now applying the divergence theorem to state Coulomb's law or Gauss law from the Coulomb's law. Just like you have seen, and I think that is pretty clear, because we have seen that we have been able to derive to get the Gauss law from using the divergence theorem from what this equation says, that the charge enclosed is defined from the flux density. And lastly, point 3 says that Gauss law provides an easy means of finding electric field strength or electric flux density for a symmetrical charge distribution, such as point charge, infinite line, infinite cylindrical surface charge, and a spherical distribution of charge. And a continuous charge distribution has rectangular symmetry if it depends on X, Y, Z, of course, and cylindrical symmetry if it depends only on rho, and spherical symmetry if it depends only on R. So notice we are saying 3 important points here regarding the 3 possible symmetries. You might have the rectangular symmetry, and I think I should highlight this because they are important and because they have different characteristics. The rectangular symmetry, it depends on X, not all of them, or Y, or Z. Then we have the cylindrical symmetry that depends only on rho, and the spherical symmetry that depends only on R, only. The symmetry is dependent on rho, or rather on theta and phi. It is dependent on Z and phi for the rectangular or for the cylindrical symmetry. You will see that shortly, so don't worry. You'll see how each of those points that I have reiterated are going to be evaluated or to be clearly visible. And there's another point that we are saying here, that we have said that we can use Gauss law to find E or D, but we can only use it if the charge distribution is symmetric. So again, this is the point that I normally highlight in red, that we can only use Gauss law if the charge distribution is symmetric or it has rectangular symmetry, cylindrical symmetry, or spherical symmetry. If it doesn't, then you cannot use Gauss law. But there's something that we are saying, that the Gauss law holds, which says that the charge that is passing through, the flux that is passing through a cross surface to be equal to the charge that is enclosed. That always holds, whether it is symmetric or not. But you cannot use Gauss law to find E or D unless the charge distribution is symmetric. That point you'll see it shortly, so don't get worried. And that is the point I'm actually trying to say here, that we cannot use the Gauss law to determine E or D when the charge distribution is not symmetric. So there's another point that this figure up here illustrates. It is already the point that I think I already illustrated earlier, but nevertheless, I will mention it again. I said earlier that if this cross service has charge some 10 nanocoulombs and then 5 nanocoulombs, and then we are passing some flux. We're passing some flux. The flux that will go through this volume will only be equivalent to the sum of these two. So 10 nanocoulombs minus 5 nanocoulombs, that gives you 5 nanocoulombs. So the flux that will go through here will only be equivalent to 5 nanocoulombs. And so we might only have probably a few lines, two of them that are equivalent to 5 nanocoulombs, or 3 or 4. On the other hand, if, and I'm saying if and only if there is no charge, assume now my flux is going up, that I escape the other diagram. If there is no charge here, there is 0 coulombs inside that, then there will be no flux that will go pass through there. They actually assume like it's a stone that is blocking the light. So I normally use the example of if this is a wall, this is a wall that has some 2 holes, like you can see there. Then the amount of light that will, if you shine the light along this direction, the amount of light that will come out of this one is the only one that is equivalent to the light that can pass through the 2 holes that are there. Okay, so that is the Riemann illustration of. But then if this diagram, if this figure V2 is completely opaque, cannot allow any light, then that means it doesn't have any charge, and therefore no flux can pass through. For me, that I think is a good way, or a Riemann way of illustrating the flux density, the flux, the Gauss law, etc. So if you have not understood that, review the recording and you will somehow see what we are trying to say. So we have said that we cannot use Gauss law to illustrate the points. Okay, we cannot use Gauss law to calculate E or D if the charge distribution is not symmetric. We have said there are 3 types of symmetry. The rectangular symmetry that depends with either either Y, X, or Z, or rectangular symmetry that depends only on rho, or spherical symmetry that only depends on R. Yeah, so that serves to introduce the Gauss law and its application. So, but now we want to do some practical applications of Gauss law with some typical surfaces that we have discussed before. And the first service has been infinite line. Another one has been finite line. Another one has been infinite sheet of service, or a finite volume. These are the 4 typical volume. What do you call them? The 3 typical elements that we use to evaluate probably Coulomb's law or Gauss law, and I guess they are very, very important. but a glass of water before we continue. Then applications of Gauss law. And you see now that the procedure for Gauss law to calculate the electric field involves first knowing whether symmetry exists. That is a point we have overemphasized in our introduction to Gauss law. So we must always have symmetry existing before we apply Gauss law. Now, once it has been found that symmetric charge distribution exists, we construct a mathematical cross service, which is called the Gaussian service. Then the service is chosen such that D is normal or tangential to the Gaussian service. When D is normal to the service, then dot product of D and the differential service always gives us a scalar product, which is D and the elemental service area, because D is perpendicular to the service. When D, on the other hand, is tangential to the service, then we know that tangential or the dot product of two services that are in parallel always gives you a 0. Thus, we must choose a service that has some form of symmetry exhibited by the charge distribution. The choice of an appropriate Gaussian service where there is symmetry in the charge distribution comes from the intuitive reasoning and a slight degree of maturity in the application of Gauss law. Now we are going to apply the basic ideas in the following cases. The first case is the point charge. And with point charge, we say suppose charge Q is located at the origin. To determine D at a point, it is easy to see that choosing a spherical service containing P will satisfy a symmetric or symmetry condition. So again, as I already mentioned, we are always, the first question is to choose the kind of symmetry you want to work with. We are saying that we have, where am I? We are saying that we have a point charge, Q. If you wanted to find the electric flux density due to Q, we need to find a service or a Gaussian service, because we said D is dependent on the service of observation. So it's a matter of cross service. Remember what the Gaussian rule has said, that if you want to find the flux that is passing through a cross service, you must find the charge that is enclosed therein. Therefore, if I want to find a Gaussian service, we are saying that the best Gaussian service that would describe the flux density that is flowing through a service that is enclosed by a charge, which is point charge, then the best one is spherical. So a spherical is the ones, so now selecting spherical symmetry was the first step. So that is the first step we have done. So we have said that point charge is best described by a spherical service, which is containing P of course, I'm saying that we want to observe the flux at point P, which is a surface surrounding a point charge Q. And we are saying the best surface to work with is spherical. Now, thus, a spherical surface centered at the origin is the Gaussian surface in this case, and is shown in figure 413. So I believe we have a figure 413 here. We have a point charge Q that is, we want to observe the electric flux density at point P, and P could be anywhere along the Gaussian surface. Now, since D is everywhere normal to the Gaussian surface, that is D is equals to dRAR, applying Gauss law, which is the flux passing through that the enclosed surface is equals to the total charge enclosed in the surface, it gives us this equation 4,4. That simply says that the flux dot the elemental surface you integrated over the closed surface will give you the radio. When I say radio, please get that radio means the outward from the center. So dr is the one that you're describing. It is pointed towards the radio distance or the radius. It is coming from the word radius. So when I say radio, it's along the radius of the sphere. Then we're saying that the charge enclosed is simply given by from this equation, and we have said that we know the dot product always gives us a scalar product, but since dr is independent of the surface, then we actually integrate over the surface, and we have the surface of a sphere is obtained by 4 pi r squared, and therefore Q becomes equals to this term. And therefore, our objective is to obtain the flux density at point P. So therefore, it's going to be dr pointed towards the direction of the AR, and you're saying it is going to be equals to, if you divide by both sides by 4 pi r squared, 4 pi r squared, then you are going to find Q all over 4 pi r squared in the direction of AR. And that equation, of course, comes in agreement with what equation 4.5 says, that the electric flux density due to a point charge Q at point P can be described by equation 445, that simply evaluates the D as at distance r from Q, and you of course get equation 445, giving you the value of D. Notice that it is a vector; it is pointing towards direction AR. And therefore, at any point, you can always find the electric flux density D from the point